In this video, we're going to discuss how to solve trigonometric equations using identities. When a trigonometric equation involves more than one trigonometric function, we may need to use identities to convert all expressions to involve just one of the functions. Let's consider an example. This problem asks us to solve the equation sine squared theta minus cosine squared theta equals 1 plus cosine theta in the interval 0 less than or equal to theta less than 2 pi. This equation is quadratic in form. However, the presence of both a sine and cosine function makes previous techniques, such as factoring, not possible to use, at least initially. We need the equation to contain only sine terms or only cosine terms if we wish to factor. Since the equation given has a linear term involving cosine, then we will get the equation completely in terms of only cosine theta. And to accomplish this, we will need to write the sine squared of theta in terms of cosine. Now, from the Pythagorean identity, we know that sine squared of theta plus cosine squared of theta equals 1. Therefore, sine squared of theta equals 1 minus cosine squared of theta. And replacing sine squared of theta in our equation with 1 minus cosine squared theta, we have an equivalent equation of the form 1 minus cosine squared theta minus cosine squared theta equals 1 plus cosine theta. And now we have a quadratic equation in terms of cosine. So let's get 0 on one side. Now I'm going to subtract 1 from both sides of the equation and subtract cosine theta from both sides. And combining like terms, we have the equivalent equation negative 2 times cosine squared theta minus cosine theta equals 0. I personally don't like having a leading coefficient that is negative on the quadratic term, so I'm going to divide both sides of the equation by negative 1 and write 2 cosine squared theta plus cosine theta equals 0. And now we can factor out a common cosine theta term, and we have the equation cosine of theta times the quantity 2 cosine theta plus 1 equal to 0. Now we use the zero product principle and we can set each factor equal to 0. So we have cosine of theta equal to 0 and 2 cosine theta plus 1 equal to 0. So now we have two linear equations and we need to solve each one for the cosine term. Now the first one's already there. We have cosine of theta equals 0. The second equation of 2 cosine theta plus 1 equals 0 will become cosine of theta equals negative 1/2. In the interval of 0 less than or equal to theta less than 2 pi, we know that cosine theta equals 0 when theta equals pi over 2 and 3 pi over 2. And we also know cosine theta equals negative 1/2 when theta equals 2 pi over 3 and 4 pi over 3. So in summary, our original equation of sine squared theta minus cosine squared theta equals 1 plus cosine theta has a solution set of pi over 2, 2 pi over 3, 4 pi over 3, and 3 pi over 2 in the interval 0 less than or equal to theta less than 2 pi. This problem asks us to solve a trigonometric equation using identities. The equation is secant squared theta plus tangent theta equals 0 in the interval 0 less than or equal to theta less than 2 pi. We need the equation to contain only secant terms or only tangent terms. We can't have a mixture of both. And since the equation has a linear term involving tangent theta, then we're going to get the equation in terms of only tangent theta. So we need to write the secant squared of theta in terms of tangent theta. Now from the Pythagorean identities, we know that secant squared of theta equals 1 plus tangent squared of theta. So replacing the secant squared theta term in our equation, we get an equivalent equation of 1 plus tangent squared theta plus tangent theta equals 0. And reorganizing terms and decreasing exponents, we have tangent squared theta plus tangent theta plus 1 equals 0. Now this equation is quadratic in form, like x squared plus x plus 1 equals 0 for x equal tangent of theta. Recall that for any quadratic equation of the form a times x squared plus b times x plus c equals 0, the quadratic formula provides the solutions as x equals the opposite of b plus or minus the square root of the quantity b squared minus 4 times a times c, all divided by 2 times a. Now for the quadratic equation in this problem, we have a equals 1, b equals 1, and c equals 1. And we could see that the term under the radical, that we call the discriminant, is going to be b squared minus 4ac, which equals negative 3. Since we're going to have the square root of a negative number, then our solutions are not real valued. They will be complex numbers. Therefore, our trigonometric equation has no real solutions. So we write that the solution is the empty set.